Today we're going to talk about limiting reactants and percent yield, and we're going to use a recipe for French toast to introduce this idea and then apply it to a chemical recipe. Essentially, which is a chemical reaction. So if you take a look at what is given here, we're given two reactants, and I can figure out my limiting reactant. And what that means is which reactant is going to run out first. That's my limiting reactant. In life, probably the most common limiting reactant would be running out of gas in your car, and if that runs out, then that reaction stops and your car doesn't move anymore because you don't have any gas to keep going. If that chemical reaction stops, then you don't have any energy to keep it moving. So I'm going to use both reactants given to try to figure out how much product I could make. So based on this equation, this is my given, and then my ratio here is 1 cup of milk per 16 pieces of French toast. And down here, for every 16 pieces of French toast, my ratio is 4 eggs that I would use. If I use this process, this would give me 36 pieces of French toast. Just by taking 2 1/4 times 16, this would give me 40. So my limiting reactant is going to be my reactant that gives me the least amount of product. So in this case, the answer would be milk. It gives me the smaller amount here, the 36 pieces of French toast, and that would be called my theoretical yield, the smaller amount. Because once it makes 36, it doesn't matter how many eggs I have or how much bread I have. The milk's gone. There's no way I can make more than 36 pieces of French toast. Now, that's the answer to number 2 then, how much French toast could be made. So is 36, that's also known as a theoretical yield. Percent yield, and we're going to apply it to French toast, and then we'll do the whole back looking at it for a chemical recipe. But for percent yield, is going to be actual yield. This will be a equation you'll need to know. Actual yield divided by theoretical yield. Theoretical yield times 100%. And that's just to move the decimal over and get a percentage sign over it. So in this case, if I was going to plug in my data, 33 pieces of French toast, so I'd have to give that to you. Or in a lab, you would have to actually find an actual yield. But if it's a problem on a quiz or a test or a worksheet, I have to give you the actual yield. Theoretical yield you can get from using stoichiometry, like we just did. So I take that by 100%, and I believe it gives me 92% yield in this situation. So you might say, well, why wouldn't I get 36? Well, in the case of a recipe, maybe some of the French toast got too much batter on it, or you dropped a piece of bread and you didn't get quite the 36 pieces of French toast that you expected. In the case of a chemical reaction, what would cause you to not get all of the reactant or the product made would be the fact that not every single reactant will find another reactant to collide with, and we are unlikely to get 100% of the product made that we would expect because of that. So in this problem on the back, I just balanced it quick, so you want to do that on your sheet. But in this problem, we are giving the two reactants of oxygen and ZNS. The question is what's to be the limiting reactant. And if it was a standalone problem where there wasn't any future questions to it, then I would just solve for one of the products each time with these reactants, like I did on the front with the French toast. I could pick the ZNO and solve for grams or moles. Moles would probably be easier, less steps. Or I could solve for grams or moles of sulfur, but I'd have to be consistent and keep the same product each time. But since the next question is asking me the theoretical yield in grams of zinc oxide, I'm going to go ahead and solve for that right away. So then I know once I get my smaller number, I will have my theoretical yield. So I'm going to solve for grams of zinc oxide because of that. And don't get caught thinking, hey, there's way less oxygen here, so there's no way that that's not going to run out first. So you might think that this is for sure going to run out first. That is not always the case. So you got to go through the math and check it out. So now it's a gram to gram stoichiometry problem like we've already done. And I'm just going to fill in the blanks here. And moles of ZNS need to cancel here. This is grams of ZNO, so there's going to be 1 mole of ZNO. This is going to be moles of ZNO. balance equation, these are both 2's. If I add up the grams from periodic table, the molar mass, so this is 97.45. This is 81.39. Just notice I'm keeping the same product on both of these. So this will be 81.39. This will be 1 mole of ZNO. This will be moles of ZNO. This is now going to be oxygen. So I'm going to figure out with each of my reactants how much product could I make. One of them will run out first. Just ignore that for right now. That's annoying, but we're going to go ahead and ignore it. Otherwise, everything would have to be erased. So now for my balance equation, this is a 1, and this, just like it was up here, is a 2. The answers that I get in this situation, I actually get 38.8 grams on this of the ZNO, and here I get 67.7 grams of ZNO. So which one is actually limiting me? That's the ZNS. What my theoretical yield is this right here. This is my theoretical yield, the 38.8. That's my smaller value of the 2. So that is my theoretical yield. This is my limiting reactant. So then when I solve for the percent yield in number 3, I am going to use that theoretical yield to do that. So in the case of number 3 down here, percent yield is equal to what they're giving me for an actual yield is 18.4 grams divided by the smaller number, which is the theoretical yield from the last problem, times 100%. And the yield is not super awesome in this point, but should be less than 100% typically. And we'll talk about why that wouldn't be, but in this case, that would be the percent yield of this reaction.